Hello to all my viewers. This is Dr. Dhaval Maheta, and today we are going to understand how to run discriminant analysis in SPSS. Discriminant analysis is a statistical technique used to classify a set of observations into predefined classes. It is used when the outcome variable is categorical and the predictor variables are continuous. Let's see the difference between discriminant analysis and logistic regression. We start with the purpose. It classifies observations into predefined classes. In case of logistic regression, it estimates the probability of an observation belonging to a class. Assumptions assumes normal distribution of the predictor variables and equal covariance matrices for linear discriminant analysis. No assumptions about the distributions of the predictor variables. So we can say that this is parametric and this is non-parametric. Type of decision boundaries: linear or quadratic decision boundaries. In case of logistic regression, linear decision boundary, logit function in the log odds scale. I have already explained the concept of odds ratio, and exponentiated coefficient in my previous video of logistic regression. Kindly refer to my playlist. Covariance assumptions assumes equal covariance matrices or different covariance matrices. So QDA stands for quadratic discriminant analysis. No assumptions about the covariance matrices. Interpretability provides discriminant functions which can be interpreted in terms of separating the classes. This provides odds ratio and probabilities, often easier to interpret in terms of likelihood. That's the reason sometimes discriminant analysis is considered to be the black box. Because the equation which we can form in logistic regression, this is not possible in case of discriminant analysis. Here we get a clear-cut equation handling nonlinearity, limited to linear or quadratic decision boundaries. Here can handle nonlinearity with transformations or polynomial terms. Computational complexity can be more complex with large data sets, especially for quadratic discriminant analysis. Generally, less computationally intensive compared to quadratic discriminant analysis. The example is medical diagnosis classify patients into high risk or low risk of a disease based on features like age, blood pressure, and cholesterol levels using LDA. Credit scoring predict the probability of customer defaulting on a loan based on financial metrics like income, credit score, and loan amount using logistic regression. Now, when to use discriminant analysis and when to use logistic regression, it depends on the multivariate normality for which we will be performing box M statistics. So when we get multivariate normality, then we run discriminant analysis, and we don't achieve the multivariate normality, we go for logistic regression. Applications of discriminant analysis: medical diagnosis. Classify patients into different disease categories based on diagnostic tests and clinical measurements. For example, distinguishing between the types of cancers based on tumor characteristics. Finance. Assess whether an individual is likely to default on loan or credit card based on financial history, income, and other relevant variables. Marketing. Segment customers into distinct group based on purchasing behavior, demographics, and other attributes. This helps in targeting marketing strategies more effectively. Biology and ecology. Classify plant or animal species based on measurable characteristics. For example, identifying fish species based on their physical traits. Manufacturing. Classify products into acceptable or defective categories based on measurements taken during production. This helps in maintaining product quality and reducing defects. Education. Classify students into performance categories. The example is high, medium, low, based on academic metrics such as test scores and attendance. Social science. Classify individuals into different behavioral types or psychological profiles based on survey data and psychometric tests. Environmental science. Classify areas based on levels of pollution and environmental impact which can guide regulatory actions and resource allocations. Sports analytics predict the outcome of sports matches based on historical performance data and other relevant factors. Assumptions of discriminant analysis. We start with the normality. The predictor variables are normally distributed within each class. This is basic assumption. We can run discriminant analysis only in the scenario in which we achieve the multivariate normality. If the multivariate normality is not achieved, then we run logistic regression. This assumption implies that the distribution of each predictor variable, when conditioned on a class, follows a normal Gaussian distribution. Equal covariance matrices. The covariance matrices of the predictor variables are equal across all classes. I have already explained the concept of variance and covariance matrices in my previous videos. Kindly refer to it. Linearity. The relationship between the predictor variables and the class membership is assumed to be linear. Independence. Each observation is assumed to be drawn independently from the population, and the observations of one class do not influence those of the another class. Homogeneity of variance. This assumption ensures that the scatter or spread of the data within each class is similar. If the variances are significantly different, it might be better to use quadratic discriminant analysis or another method that does not assume equal variance. Multicollinearity. High correlation among predictors can lead to issues in estimating the parameters accurately. LDA assumes that the predictor variables are not highly collinear. Number of observations. Small sample size can lead to overfitting and unreliable results. Adequate sample size ensures that the estimated means and covariances are stable. Now we'll take one case study. Company provides a broad range of services and products to customers around the world. Company wants to understand the nature of customer complaints based on geographic location. It is crucial for improving customer service. To analyze this, various types of complaint have been noted down, and the dependent variable is a geographical location of the customer. 0 is for the customers which are inside the North America, USA, North America, and 1 is outside North America. So basically, we want to segregate the complaints according to the region. By identifying the significant complaints from each region, we aim to enhance our service offerings and address the regional issues more effectively. So this is the data set. The same data set we will see in the SPSS. Our dependent variable is 0 stands for inside North America, 1 is outside North America. What are the different complaints which we are getting? I'll explain this. Product quality, we start with X6, product quality, e-commerce, technical support, complaint resolution, advertising, product line, sales for image, competitive pricing, warranty and claims, new products, orders and billings, price flexibility, delivery speed. Now they have all been measured on the scale of 0 to 10. 0 stands for poor, 10 stands for excellent. And this is your data, the dependent variable and the independent variable. Okay, now how to run discriminant analysis? So for this, we will go in analyze, classify, discriminant. Now our dependent variable is region. We have to specify the range. So for this, go in variable view and see the coding. 0 is minimum, 1 is maximum. Now click on define range. Right down here, 0 and here 1, continue. Now activate the stepwise method. Go in statistics, click on means, univariate ANOVAs, box M, Fisher's function coefficients, unstandardized, continue. Method, In this, activate Mahalanobis distance. Continue. Classify. Activate summary table. Continue. Now, transfer all the independent variables. So, from x6 to x18, transfer it here. Click OK. So now we got the result. This is the group statistics, test of equality of group means, and this is your box M test. We always start with box M test. Basically, it checks the multivariate normality. So I'll copy both of this on the slide and let's start the interpretation. Box M test tests the null hypothesis that the covariance matrices of all groups are equal. This is a key assumption in the linear discriminant analysis and other multivariate methods. So, multivariate normality, it's basically a test for multivariate normality. Now here we got the p-value less than 0.05. Given the p-value of 0.00, we reject the null hypothesis that the covariance matrices are equal across the groups. Now this is not desirable. Okay, what we want is this p-value should be more than 0.05, then only we can run discriminant analysis. But just for understanding purpose, we will proceed further. This suggests that the assumption of equal covariance matrices in the LDA is violated. Okay, the multivariate normality is not present. Let's proceed further. Test of equality of group means. See the p-value of x6, x7, x10, 11, 12, 13 and 17. They are all less than 0.05, which is desirable here. See, in case of box M test, p-value should be more than 0.05. In case of test of equality of group means, it should be less than 0.05. So as the p-value of the product quality, x6 e-commerce, x7 advertising, x10 product line, x11 sales for image, x12 competitive pricing, x13 price flexibility, x17. They are all less than 0.05, which means that these variables significantly contributed in differentiating between two groups. So the mean of product quality, e-commerce, advertising, product line, sales for image, competitive pricing, price flexibility differs significantly in two groups. Which are the two groups? Inside the North America and outside the North America. And basically, we can say that these are the complaints which are having a different profile inside the North America and outside the North America. Eigenvalues. A higher eigenvalue indicates a more significant function in terms of explaining the variance between the groups. Here, the eigenvalue of 1.59 is relatively high, suggesting that this function is quite effective in distinguishing between these groups. Percentage of variance. Since the first function, this one, explains 100% of the variance, it indicates that this function captures all the information needed to separate the groups in this analysis. This implies that the function is highly effective for classification purposes. Canonical correlation. I have already made the video on canonical correlation. Kindly refer to my playlist. The canonical correlation of 0.777 indicates a strong relationship between the discriminant function and the separation of two groups. Values closer to 1 suggest a stronger relationship. So a correlation of 0.777 is quite good, showing that the discriminant function is effective at classifying cases into the correct groups. Now this eigenvalues, you will get it from here. It will be at the fag end. Here is it. And here only you will get the Wilks lambda. Now we will do the interpretation for Wilks lambda. Now just see this image. Wilks lambda close to 1. We are not able to segregate the groups C1, C2, C3 because there is too much overlapping. Wilks lambda close to 0. we can segregate the groups very easily, that this is a red group, blue group, and green group. So we want that the value of the Wilks lambda should be nearer to 0. Now let's check. In our case, it's 0.397, chi-square 180.178, and the p-value less than 0.05, which is desirable. So Wilks lambda ranges from 0 to 1, where values closer to 0 indicates that the discriminant function explains a large proportion of the variance between the groups, and values closer to 1 indicate less explanation. The Wilks lambda test results indicate that the first discriminant function significantly differentiates between the groups. The low value of Wilks lambda combined with the high significant chi-square statistics and a p-value of 0.000 means that the discriminant function is highly effective in classifying cases into their respective groups. So here p-value less than 0.05 is desirable, and the Wilks lambda, its value should be nearer to 0. Now we'll talk about standardized canonical discriminant function coefficients. So this, I'll get it from here. Wait a minute. Yeah, here is it. Standardized canonical discriminant function coefficients. Now let's do the interpretation of this. So in this case, we are having positive values and negative values. Positive coefficients. Variable with positive coefficients, which are sales for image, competitive pricing, price flexibility, increase the score on the discriminant functions, indicating that the higher values of these variables are associated with the higher likelihood of belonging to the group characterized by the high function scores. Negative coefficients. Variables with negative coefficients, product quality, e-commerce, product line, decrease the score on the discriminant functions, suggesting that the higher values of these variables are associated with the lower likelihood of the belonging to the group characterized by the lower function scores. Importance. The magnitude of the coefficients reflects the relative importance of each variable in discriminating between the groups. Variables with large absolute values, either positive or negative, have a great influence on the discriminant function. Now let's understand this. Positive coefficients. Higher likelihood of belonging to the group characterized by the higher function scores. So we want to achieve the higher score in this, and here the score will be low. So all those complaints which are having positive values, they are contributing towards 1 is equal to outside North America, and all those complaints which are negative, product quality, e-commerce, product line, they are all negative. Sales for image, competitive pricing, price flexibility, they are positive. So negative contributes towards 0 inside North America, and the positive contributes towards outside North America. This means that these are the complaints specific to the positive one is outside North America, and these are the complaints specific to inside North America, outside and inside. Structure matrix. This is available from here. Structure matrix. The structure matrix table provides a correlation between each predicted variable and the canonical discriminant function. This matrix helps to understand how well each predicted variable correlates with the discriminant function, and therefore how much it contributes to the differentiation between the groups. Loadings exceeding plus or minus 0.40, plus or minus 0.40. Okay, so let me introduce 0 here. That will be much better. Are considered substantive for interpretation purpose. Strongest correlation. Variables with the high absolute correlations, either positive or negative, are competitive pricing and price flexibility for positive correlations. So competitive pricing, positive, price flexibility, positive, product quality and product line, they are negative, but they are more than plus or minus 0.40. So product quality and product line for the negative correlations, These variables are the most influential in differentiating between two groups. Moderate to weak correlations. Variables like sales for image, advertising, e-commerce, and other have a moderate to weak correlations indicating a lesser but still noticeable impact on the discriminant function. Minimal impact variables. Variables such as order and billing, new products, delivery speed, and complaint resolutions have a minimal impact on the discriminant function, suggesting that they are less useful for distinguishing between the two groups. Or we can say more or less, complaints in both the groups are similar or their means are similar. Canonical discriminant function coefficients. Now we want to make the equation. So this is available here. We will make the equation from this. The canonical discriminant function equation is region is equal to, we start with constant, minus 1.854 minus 0.238 into the product quality minus 0.536 into e-commerce, just refer here, minus 0.372 into the product line plus 0.763 into the sales force image plus 0.322 into the competitive pricing plus 0.372 price flexibility. Now the region, its value can be 1 and 0, right? So when I can achieve 1, which are the variables which contribute towards 1? All positive 1. And the 0, they are all negative ones. The function at group centroids. The function at group centroid table shows canonical discriminant values for each group based on the group means of the predictor variables. Now see these values. It should be far apart so that we can say that we are able to differentiate between the two groups very easily. If the centroids are nearer to each other, there is a lot of overlapping and segregation is not possible. This value indicates where the centroids or average discriminant functions of each group fall on the discriminant function. USA North America, that is inside North America. The discriminant function score for the USA North America group is minus 1.487. A negative value indicates that on average, cases in this group have a lower class on the discriminant function compared to other group. Outside North America. This is the discriminant function score of outside North America group, which is 1.012. A positive value indicates that on average, cases in this group have a higher score on the discriminant function compared to the North America. Now we will have to understand this classification table. So first of all, we will see the classification results are available here. Okay. Now let's do the interpretation for this. Original data, USA North America, that is inside North America, and this is outside North America. The prediction done by the discriminant function inside North America. So 80 are such cases in which the observed data is inside North America and the prediction done by the function is also inside North America. So this is correct classification. The second one, the original data is outside North America and the prediction done by the function is also outside North America. So we are having 99 such cases. So 80 plus 99 are correctly classified cases. Now, the original data shows that it is outside North America and the prediction done by the model, the function, is inside the North America. So there are 20 such cases. Okay. The another possibility is that the original data is inside the North America and the model predicts outside the North America. So 20 plus 1. These are misclassification in the data or also known as a leakage in the model. Classification results is a simply summary of number and percent of subjects classified correctly and incorrectly. 80 plus 99 is equal to 179. 179 divided by 200. 200 are the total number of observations is equal to 0.895. This means that it is 89.5% of the cases are correctly classified into their respective groups. It's quite good. Any number which is more than 70%, it's quite good. Classification accuracy should be more than hit ratio. Now, what is this concept of hit ratio? Let's understand. We are having only two groups. That is, the dependent variable is having only two groups, 1 and 2. So what can be the nature's probability? 50%. So what we want, that our classification accuracy should be at least more than 50% plus 50%, 1 by 4. 1 by 4 remains as it is. Here we are inserting the probabilities. So 50% plus 50% into 1 by 4, I will get 62.5%. So this classification accuracy, which I got 89.5%, which is rounded off to 90%. So 90%, this classification accuracy should be at least more than the hit ratio. Now, if we are having three outcomes, let's say stage 1 of cancer, stage 2 of cancer, stage 3 of the cancer. So what is the nature's probability? 33%. So what will be the hit ratio in this case? 33 plus 33 into 1 by 4, whatever figure I will get. So this is to be considered here, right? So my classification accuracy should be more than that. Now let's go in the data. It has given me the group membership. Just a minute. If you don't get it, no need to worry. Click here, go in discriminant analysis. You'll require a group membership here. So go in save, click on 1, 2, 3, continue, click OK, and just wait for a second. Got it? Yes, we got it. 1. So discriminant scores from function 1. Okay. Now what I'll do, I'll simply drag this and bring it near to x4. Yeah, here is it. Now this is your original data, and this is the prediction done by the function. In first case, the original data is outside North America, and the prediction done by the model is also outside North America. So this is correct classification. Second, inside North America, this is the prediction done is also inside North America. So this is also correct classification. Now we talk about the third case. Original data outside North America and the prediction done is inside North America. This is what is your leakage in the model. This. So we are having 20 plus 1, 21 such cases in which the leakage happened. Now there can be another possibility also, that this side it's USA North America and here I get outside North America. So this is also the leakage in the model. Okay. So this was all about how to run discriminant analysis in SPSS. For more videos on advanced data analysis using SPSS, kindly subscribe to my channel. You can also refer my playlist in which I have uploaded videos on data science, machine learning and artificial intelligence. Please don't forget to like and share my videos. You can also follow me on different social medias, link given in the description box.